Start teaching now? Yes, okay. Let me grab my whiteboard markers. So today I'm going to continue. I want to cover, talk about second derivatives. I want to talk about integral calculus. And then, so here we talk about line integrals. Talk about surface integrals and also volume integrals. If I have time, I will talk about the fundamental theorem of calculus. Okay, so the first part is second derivatives. Okay, so as it's kind of obvious from the name, second derivative means applying derivative two times. Okay, for a simple function, one-dimensional function, that's very trivial, and that means if you have a function of x, okay, the first derivative is df over dx. Okay, so this is going to be the slope, and then you will have the second derivative, d2 of x over dx2. Okay, so technically this is a function, this becomes the slope, and this tells you the curvature. Okay, and in physics, if you go and use the second derivative, technically you are coming up with a different physical quantity. Okay, if fx is the position, df over dx becomes velocity, and the second derivative with respect to time becomes acceleration. So you really come up with the different variables and different functions, and a lot of time in physics, because the variable you are taking derivative with respect to has a physical unit, so you will come up with something very different physical unit as well. Okay. Now, this is for simple one-dimensional function. You have used that a lot in physics, I'm sure in mathematics and everywhere as well. Very trivial concept for you. Now, what we want to do today, we learn about the del operator, right? So the del operator is the partial derivative with respect to each direction times the unit vector. Okay. So we have this del operator over C. Okay, and now we want to apply these two times on three-dimensional functions. They could be scalar functions or they could be vector functions. Okay. So if we do it once, we already talked about that. There are three different ways that we can apply the del operator on a function, on a three-dimensional function or two-dimensional. And you can apply it on scalar fields, and the only way you do that is the gradient, right? So if we do it once, we can get something like gradient of t. Okay. We can apply it on vectors in two different ways. And that is the divergence of a vector function or the curl of the vector function. Okay, so now we have really three different ways to apply the del operator once on a function. Okay, so now think about this. If you want to apply it twice, how many different ways do we have? Let's say we have the gradient of t, and then we want to apply the del operator a second time on the whole thing here. How many different ways you can do that? Say something. The gradient of t, is it a vector or a scalar?
Vector.
This is a vector, right? So this is, as a combination, this is a vector. You can apply del operator on a vector in actually two different ways, okay? So technically this becomes two different ways you can apply the del operator twice. One of them is the dot product, and that becomes del dot gradient of t. This is one way. Another way is doing the cross product, del cross gradient of t. Okay, so these two things I wrote here are second derivatives. Okay, and then we can continue on these ones as well. We have divergence of v. Divergence of v, is it a scalar or is a vector?
Scalar.
Is a scalar. So there's only one way we can apply a del operator for a second time, and that is taking gradient of this, okay? We cannot do another dot or curl, okay? So we can take the gradient of divergence of v, okay? And then we have the third one, which is the curl of v, okay? And if we take derivative for the second time, as a whole, it's a vector, so we have two options. We can take the divergence of the curl, or we can do curl of the curl. Okay, so these 5 second derivatives are actually the whole options we have to apply del operator twice on a vector or a scalar field. Okay, again, the v here are vector functions, and t here is a scalar function. Okay, now looking at these 5 second derivatives, some of them are popular, happen a lot, some of them are rare, and some of them are just zero. Okay, so for the next 10 minutes or so, I'm going to talk about each of them separately. Okay, some of them deserve more discussion, some of them don't. Okay, so let's start from the very first one. Okay, the divergence of gradient of t. Okay, so how would you want to expand this? Okay, what does it really mean? Think about t, it's a function, okay, function of 3 variables, function of x, y, z, okay, and then we are taking the gradient and then divergence, okay. How do you expand this? I would just write components, okay. So what I do is that I take this one, okay, I'm gonna put a star on this so that you know which one I'm discussing, okay, a star, and I'm gonna expand it here, okay. So the del operator has 3 components, x hat d over dx, y hat d over dy, z hat d over dz. Okay, so gradient of t is each of these derivatives. At the same time, we have this del dot, so we are doing the dot product. Let's write the del operator in terms of the components. Okay, so I have x hat here, d over dx plus y hat d over dy plus z hat d over dz. Okay, sounds good. So this is the del operator, and I do the dot product times now the gradient of t. It has 3 components again, and then we have x hat times dt over dx plus y hat dt over dy plus z hat dt over dz. Looks good? Okay, but it's very long. Doesn't look that good, okay? But we can simplify this very easily. This is the dot product, okay? For the dot product, what you do is that you multiply like components and then add them algebraically, okay? So this x hat components times this x hat component, we have this derivative, and that's gonna take effect on this term, okay? And that means from the x hat component, what we have is the second derivative, d2t over dx squared, okay? So this is the first component. And the second component, y hat, and this term takes effect on this term. That means one derivative with respect to y is going to affect on this, and then we get very similar to the x component, we get d2t over dy2. Okay, so the second derivative of t with respect to x plus second derivative of t with respect to y, and I'm sure you can guess the last term should be the second derivative of t with respect to z. Okay, so this is the divergence of the gradient of t that becomes a scalar, okay, and that has three terms, second derivative of t with respect to x, y, and z. Okay, so this is the three terms we get. Okay, so this one, another way the notation people use it is like this, del 2t. Okay, and this is acting on a scalar function and giving a scalar. Okay, are you familiar with this? Anyone has seen something like this before? Okay, if you haven't seen so far, you will see a lot because it happens a lot in physics. And this is in fact called Laplacian. Okay, so this is a Laplacian of the function t. Okay, this happens very often in physics, in all fields of physics. In mechanics, we use that for wave. And in fact, it happens in every type of wave. In the wave equation has a Laplacian term. You will see this in other parts of physics as well. In thermodynamics, you will see that a lot. When temperature is diffusing, when the heat is diffusing, the way it diffuses and the way the temperature changes follows an equation. In that equation, we have the second derivative Laplacian of the temperature. So we have it in mechanics, in electromagnetism, in thermodynamics, in quantum mechanics, we have second derivative like this as well. So this is very, very popular in physics, and this is called Laplacian. The term is technically the second derivative of the function with respect to any direction, okay, with respect to any variable, and then you add them up, okay. We also used Laplacian on vectors as well, okay, but that notation is the fact that if you're applying that on a vector, what you're doing is technically applying it on every component of that vector, okay? And the result is also vector, okay? So if I want to write that here, I'm gonna open up a window here. If you have Laplacian acting on a vector, this is, the vector is, let's say, three-dimensional vector. This is equal to the Laplacian of the x component of the vector times x hat plus the Laplacian of the y component of the vector times y hat, and then you have similar term for the z direction. Let me times z hat. Okay, so this is how you can apply a Laplacian on a vector, and this is the basic definition of the Laplacian acting on a scalar function. Any question? Okay, so I can already tell you among all these five options for the second derivative, the Laplacian is the most famous and most popular one that we see a lot in physics applications. And we see in this course as well. One of the places that we use this is electrostatic potential. We look at the Laplacian of the electrostatic potential, and that is directly related to the charge distribution that we have. Okay, so we will come up with equations that is second derivative Laplacian of the electrostatic potential is equal to charge distribution times the constant, something like that. Okay, so these things we will work with in chapter, I think, 3 or 4 of this course. Okay, Any question?
Nope.
No? Is it clear more or less? Yes? Okay. I still
Yes.
hope you have seen these things before as well, right? Am I correct or wrong?
Yeah.
Yeah.
In
Yeah.
calculus. Okay. So, but I hope it's a good reminder for you guys. Okay. So that's Laplacian. And this is the way you really expand this. Okay. So for all of these terms, the way you want to expand and study them is take this del operator, write it in terms of the components, and you can do here, we did the dot product. We can do cross product. For the cross product, you know, you have to make up a matrix and look at the determinant of the matrix. And then for the rest, you're gonna do the same, okay? So the first one I said is very special. The second one is a special in a different way, okay? The curl of the gradients, okay? Anyone knows how is this special? This is special in the sense that this is always zero, okay? So any function, any possible function, if you can take the gradient of that and then calculate curl of that gradient, it's gonna be zero, okay? And it happens all the time for every function. There's no way to escape from that, it's zero. And the way to show it zero, again, you can write it, the product in terms of the components, make a matrix, look at the determinant, you will end up having terms like d over dx of dt over dy minus d over dy of nd over dx. Okay, so if you expand this, you will have many terms, but you will see the structures like this. Okay, so what is this? This is a derivative of t with respect to y, and then the second derivative is with respect to x. And then the next term is derivative of t with respect to x. So in that sense, it looks different from this, and here is y. But as a matter of fact, these two terms are equal, okay? And they cancel out each other. At the end, you will have many terms like this, and the curl of the gradient becomes zero, okay? And this has sort of direction in physics, and that is if the curl of a field, vector field is zero, that means that's a conservative field, okay? And a lot of cases like electrostatic field, we can write that in terms of the gradient of the scalar field because we know that the curl of the electric field is always zero, okay? So that has, I don't know how to put it, but I would say indirect application in terms of how from electric field we can go to electric potential, okay? Again, these things we will talk about in chapter 4, I guess. Okay, so this becomes zero. And the third one, the gradient of the divergence, okay? So this one, I would say it's not very special. It's just very rare, okay? There's nothing specific about it. This is very rare in physics. There is nothing wrong about it, okay? So mathematically, you can take the divergence of any field and then take gradient of that. It just doesn't happen very often, okay? And so that's the case. The fourth one, the divergence of a curve. This is again a special, okay? This is a special, and we see this when we are working with magnetic fields, okay? When we have electromagnetic fields, the field can be written in terms of the curl of other fields, okay, the curl of the electric currents. And what happens is that if you expand this, very similar to the second term, it always becomes zero, okay? And the direction of this mathematics to the physics that we will work with, actually in the second part of this course, is if we have magnetic field, because we can write it in terms of the curl, always the divergence of that field is zero, okay? And the physical relation to this is that we never have any magnetic monopole. We always have magnetic dipoles, okay? So if for any magnet in your hand, if you find there should be a south and north pole, okay? There is no monopole for magnetic fields. And the mathematics here is directly related to that physical concept of not having any magnetic monopole, Okay, so this is always 0. Again, to show this, you can expand it. You can do the dot product of this del operator by the curl of V, and that's going to be a determinant. You will end up terms like this, and then that's going to be 0. Okay.
I have a question. Did you say you see this in electric field and magnetic fields, or just
This
magnetic?
one you see a lot in magnetic fields.
In magnetic field, okay.
This one you see in electrostatic fields. So if this T is electrostatic potential, that means there is no curl associated with electric field. Okay, so that's how it is. Cool. Any more question? Okay, so the last one is curl of the curl. Okay, and this thing can be expanded. This is also rare. Maybe we use it once or twice in the second part of this course. But the thing about this one is that this can be expanded and returned in terms of other second derivatives. Okay, so if you expand it, this has very similar form of the, you remember the back cap vector triple product that we talked about? Okay, so back cap was for the curl of the curl, okay? Cross product of the cross product. So this is almost the same thing. So this one can be expanded and written. You know what, let me just continue here. Because I don't want to do the expansion, I just want to write the final answer. And that can be written in terms of the, where is it? Okay, we can write it in terms of the gradient of the divergence minus Laplacian of the vector. Okay, so what we have here, this term is basically this one, the one that I said, right? And the Laplacian of V, okay, is exactly the Laplacian on a vector field that I already talked about. Okay, so this can be written in terms of the other vector product, second derivatives. Okay. And the only place I can think of we will use this is in the second part of the course when we define magnetic vector potential. Okay, so we will talk about the magnetic fields, and then we'll talk about very special potential fields from which we can calculate magnetic fields. And this is where we're going to use the solid orbits. Okay, so that's it about this. And then again, like all parts of the calculus I'm teaching these days, don't worry too much about all the details. We will use them one after one. Okay. So, but be very familiar with the concept and make sure that you are familiar with the type of the equations. And once we see them, you know where to go and look for them. Okay. Any question? Is this clear more or less?
Yeah.
Yes? Okay. So I see 2 chat messages here. Let me look at them. Laplacian, Josh. Okay, good job. Okay. All right, so we covered the second derivatives, and then I'm going to move on now to integral calculus. Let me maximize my windows again. Cool. Okay. Shall I erase the board here? Yes? Okay. Okay, so we're going to look at 3 types of integrals, okay? And what these things are, imagine you have a function, three-dimensional function. Could be a vector or could be a scalar. And we want to integrate that over a special, specific, either on a line or on a surface or on a volume. Okay. So first I'm going to write this integral separately, okay, and explain what we are integrating, okay, and then I'm going to do a step-by-step discussion of each of them, okay. So the first one is a line integral, okay. So for the line integral, you know, you can write it in terms of integral of v. V itself is a vector function, and that can be function of three variables like x, y, z, and then times dl, okay. So this is the integral of a vector function over a specific path. And that can start from one point, let's say point A, to point B in a space. Okay, if you want to imagine this, let's look at a coordinate system with X, Y, and Z. Okay, and then let's say we have a point A here. This is A, let's say it's here. Okay, and imagine we have point B in a space, and that's here. Okay, so we want to go from A to B. Okay, it's important what path we are taking. Okay, so for now, let's imagine we take a random path from this. We go from A to B. Okay, and let's imagine projection of that path on this surface is something like this. We can integrate a vector function over this path. Okay, and the way you want to think about this integral is this. Think about very small, infinitesimal step that you are taking to make one single move on this, okay? And then, of course, you are repeating that with more moves like this, okay? So the path from to A and B, let's chop it down into very small pieces. For each small step you are taking, this small step is gonna be our dl, okay? dl is a vector. It has length and it has a direction as well, okay? The step you are taking should be on the path here. And then what you're doing is that you are doing the dot product of the vector function times this small, infinitesimal small step, okay? So for each step, let's say you have a function, the function doesn't need to be in the direction of the path. Could be a function like in this direction. The next step could be a bit different and could be a bit different. For each step, what you do is you do a dot product, okay? So the dot product here becomes a scalar, and once you integrate from beginning to end, okay, you're gonna come up with a scalar as well, okay? Now I have a question. Is this sort of integral familiar to you? There is one application of this very, very popular in physics. What is that?
Work. Oh my God.
You all have seen that. If you say so, say what it is, you're saying, oh my God. This is how we calculate
Work.
Work. Okay, so work in physics is the integral of the force times displacements. Okay? So this is basic definition of the work. Force is a vector field. Displacement is a vector. The work, is it a scalar or is it a vector? It's a scalar, right? And we will use that in electromagnetism as well, when we want to relate the electric field displacement to the electrostatic potential. You will see electrostatic potential is a vector, is a scalar, and electric field is a vector field, okay? So this is the basic definition of the line integral. We use that a lot in physics in different forms. Sometimes it's very easy to do this, sometimes it can be difficult. It all depends on how your function v is defined and what is your displacement, okay? So now there's another very beautiful thing about the line integrals and path integrals like this, and that is whether they are dependent on the path or not, okay? In general, this integral not only depends on A and B, but it also depends on what type of path you are taking from A to B, okay, in general way. But there are very special set of functions, okay, and I'm saying a special set of functions, I'm referring to V, okay. There are very special set of functions that you can do this integral, and the solution at the end only depends on your start and end point, okay. So again, if I want to look at this, the work example, you can kind of think about what I mean by that. There are certain forces that if you do integral from A to B, the work is independent of the path you are taking and is only dependent on where you start and where you end. And these forces are called conservative forces, okay? So conservative forces are field forces that have this very special characteristic. If you do the line integral of them over a specific path, the result is going to be independent of the path, and it only depends on the beginning and end. In electromagnetism, the electric field has this capability, okay? It has this characteristic that any integral from any point to any point only depends on where you start and where you finish, okay? Not on the path you are taking. And because of that specific characteristic, we can define electrostatic potential, okay? So this is the line integral, and a lot of times we do line integral on a closed path, okay? So this is a demonstration of one point to end point, start and end. But we also have cases that we do integral on a closed path. And whenever we are on a closed path, technically on a loop, okay, what we do is that for the notation is that we put a circle on this integral, okay? So again, one example for this course, if we use electric field and if we do integral over closed loop, that's always zero, because electric field has this characteristic of the integral depends on beginning and end, okay? And if you go around, no matter how far you go, if you come back to the same starting point, the integral is going to be zero, okay? Because your beginning and end point are the same, okay? Magnetic field does not have this characteristic, okay? So for magnetic fields, a lot of times we do this integral over specific loops, okay? We go around it and we get something non-zero, and that's a lot of times is the way we can even calculate the strength of magnetic fields. So we do similar integrals over one loop, let's say a circle around the wire, and then we can calculate electric field, magnetic fields, okay? So this is for a loop. Any question? Is it more or less clear? Okay, and sometimes when you are carrying this integral, okay, it's a bit tricky, but you gotta be careful how you choose your DL, okay? So the way you choose your DL totally depends on how you are trying to, depends on the path you are taking, okay? So that's where the path become important. Do you want me to do one example, relatively simple example, just to show you how you choose dx, dy based on the path you are taking? How about doing that? Yes? Okay. Okay. This is an example from your textbook. So let me grab the book and okay, this is example 1.6 from the book. Okay. So let me get rid of this. And so we have the vector field of V being y2x plus 2x times y plus 1 times y. Okay, so this is the vector field we have. And then we are going from, this is x, this is y. 1, 2, 1, 2. Okay. So the question says we are going from one point A to point B. Here. So A is at 1, 1, B is at 2, 2. Okay. We are going from A to B. We want to do this integral of V dot dl from A to B. Okay, so what path we are taking? The path we are taking is this path. From A, we go straight to this point, and then we go straight to the top. Okay, so in two steps. Step 1 from 1, 1 to 2, 1, and step 2 from 2, 1 to 2, 2. Okay, my green marker is out. Okay, so this is the way we are moving from A to B. Okay, so what you should do is that you should chop this integral into two parts. The first part, you do the move number 1, and the second part, you do move number 2. And the reason we do this is that because the way you write dl in terms of dx and dy is going to be different. Okay, if you are moving in the first part, you are moving horizontally. So your dl is dx times x hat. If you move on the second part, your dl is dy times y hat. Okay, so this integral becomes integral number 1 v dot our dl in this case. So I'm gonna write number 1. Our dl is dx times x hat. What are the limits? The limit is we are moving from x equal 1 to x equal 2. That is the limit, okay? The second part of the integral is integral of v dot dy times y hat. Okay, and then here we are moving from y equal 1 to y equal 2. And this is going to be number 2. Okay, so is it legible what I wrote here? Yes? Okay, good. Okay, so we do this part. Now let's expand the first integral. The integral from x equal to 0 to x equal to 2. What is the function v? The function v has two terms, one of them in x hat, one of them in y hat. Now, what I'm doing here is I'm doing the dot product times dx x hat. So the second term that I'm doing, applying the dot product on, only has x component. Okay, so what I want to do is that I want to forget about the second part of the vector function here. Why? Because the second part is in y direction, and if I do the dot product, that's going to be 0 anyways. Okay,
I
so I want to keep the first part.
Does on the bottom of the first integral x equals 1, right? Isn't the first x a 1?
X equal 1. Yes, good point. X is moving from 1 to 2. Yes. This is 1, and this is going to be 1 as well. Thank you very much. Okay. So because I'm only moving in x direction, I keep the x component. Okay, so I'm going to keep that. I get y2 times x hat times dx times x hat. Okay, so this is a dot product. We have x hat, we have x hat. Why don't I just simplify this? X hat times x hat is 1, so I get rid of this and this. So technically we have y2 times dx. Okay, so this is going to be the first part of the integral. Okay, so what is the actual y value here? When we are moving on the first path, number 1,
Just 1.
the y is a constant. It's just 1. So that y just becomes 1. So I get this y times dx. Okay, so the first integral becomes integral of dx from x equal 1 to 2, and that becomes just number 1. Okay, so what you do is technically, this was a simple example, but what you do is that you have to make sure you can write it, your dl in terms of dx, dy, and choose your path, okay? And once you separate different parts of the path and write these things, you should come up with an integral, which is the scalar integral. Okay, so the first integral, we got this one, and that is equal to 1. For the second integral, we are moving in the y direction, okay? And that is limit of the integral from y1 equal time to y equal to 2, okay? And the dot product is here times y hat. Okay, so in the function, what I need to do is that I need to keep the second part of the function here, right? Because that's the only component in the y direction. And that is 2 times x times 1 plus y, okay? And we do it times y hat times dy. I don't want to write y hats anymore because we are doing the dot product and that's 0. And this is the kind of function I get. Now, if you are moving on the second part of the path, what is the value of x? It's 2. It's not changing at all. So it's moving from here to here. The x value is 2. So 2x that we have here, technically we can even move it out of the integral, do 4 times this. And the integral we have is 1 plus y. Okay, so that becomes 4 times 1 plus y. If you integrate it from the first term, you get y. From the second term, you get 1/2 by 2, and the limits are y from 1 to 2, and that's going to be, if you set it at 2, what do you get? You get 2 plus 1/2 times 4. You get 4 times 4, you get 16. Minus if you set y at 1, you get 1 plus 1/2. 1/2 times 4, 1.5 times 4 is 6. Am I correct? You guys check this. Whenever I do mathematics on board, I do mistake as well. So you have to correct me if I do mistake. So, and that becomes 10. Okay, so that's the second part of the integral. The integral as a whole is going to be 1 plus 10, 11. Okay. Now, there is an alternative way of doing it, going from A to B, taking a different path. Let's say you move from here to here straight, okay? Then the integral you want to do is going to be completely different. Then you have one integral on a path that your dl is dx x hat plus dy y hat, okay? So that defines your path, okay? When we went through the green path, we had 2 integrals. For one of them, dl was dx over x hat. For the other one, dl was dy times y hat. Okay. If you take the red path, you're going to get something very different. Okay. Do you want me to do that as well, so that you see the alternative way of when you change the path, how this changes? Okay, I'm going to do that too. Okay. So far, so good here. Yes.
Yes.
Okay. So let me now get rid of these. Okay. Now think about this. If you want to go from A to B straight, you are taking like 45-degree straight going up. Okay. So the dl at each step is a vector in this direction. Okay, and that's going to be dx times x hat plus dy times y hat. Okay, so it has 2 components. But since it's exactly 45 degrees, and that means we are on a line that y is equal to x, okay, this combination is going to tell us that we can write dl in terms of dx x hat plus dx again times y hat. Okay, so this line defines your path going straight from A to B at 45 degrees, and that is going on the line of y equals x. Okay, y equal x means that your dy is also equal to dx. Okay, so this is the way you really set your path. Okay. And if you want to simplify this a little bit, you can really write it in terms of dx times x hat plus y hat. Okay, this is a vector part, this is the scalar part. Okay, now if dl is this, and here we are doing one integral, because this is one straight path from A to B, the integral is, now I have my v function being y squared times x hat plus 2x times y plus 1 times y hat. Okay, this is function. And then I'm multiplying dot product by x hat times y hat times dx. Okay, so if you look at this integral, the first one, the whole term here is a vector, dot product by vector. Okay, so vector dot vector as a whole, this should be in a scalar. And that should be in terms of x, because we are now doing dx and doing this integral. Okay. Now, how do we write it completely in terms of x? The way we do it is that we know we are moving on the path that y is equal to x. Okay, so that means for every y value here, we can actually switch it to x, because that's what we have when we move on the red line. Okay, so I'm going to apply that here directly. Okay, so I'm going to, this y square, I'm going to change that and make that x square. And this one, I have y plus 1. I'm going to get rid of the y, and make it x. Okay. Now, if you look at this, we don't have any y here. We only have x. Okay. And then again, we have x hat and y hat, but because we are doing the dot product, we're going to get rid of them as well. Okay. So the integrand here, if I expand it, what I should do is that I need to multiply the like components and add them up. Okay, so from the x hat components, I get x2. Okay, and from the y hat component, the y component, I get 2x2 plus 2x. Okay, so this is the whole integrand of that. And then this is times dx and integral. Okay, what is the limit of the integrals? What limit am I moving x? From 1 to 2, right? So this integral is now a simple integral. Only in terms of x from 1 to 2, there's no vector, nothing here. Okay, so everything boils down at the end to a simple scalar integral, okay? And that's something you can do easily. So technically we have 3x2, so we have 3 by 4, no. So the first term only becomes x3. Okay, so if you take the derivative of this, you get 3x2. And the second one is 2x, so we get x2. And the limit of x moving from 1 to 2. Looks good? So now you see the integral we have in this part is very different from the one we had previously when we're moving from 1 and 2, okay? The vector function is exactly the same, okay? The starting and end point are the same, but what is different is the path you are taking, okay? And the path you are taking is going to be reflected in how you define your DL and how you define the limit for each part, okay? Was it helpful? Okay, so things like these, I want you guys to do it on your own as well, once or twice, and then they get used to it, okay? And then whenever in the course we're going to encounter the integrals like these, we do all of them step by step, okay? Any question on this?
I have a question with the integral.
Okay.
How do you get that integral? Because isn't it supposed to be x cubed divided by 3 plus?
Let's look again. Okay, I'm just doing it on board, so there's a good chance I do mistake too. So we have x2 plus 2x2, okay? So we have inside, we have 3x2, okay? So, so these two combined gives me 3x2, okay? And if you use x3, you take the derivative of this, you have 3 here. Technically, you are right, it should be 1 over 3, but we have another 3 here. The 3 times 1/3 becomes 1. That's what's happening here. Correct? And then we have 2x here. Technically, yes, integral of x is 1/2 x squared, but because we have 2 here, that becomes 1 again.
Yeah, I didn't see there was another term with x squared.
Okay. Yeah.
Yeah,
Sounds good. Any more question?
No.
No? Okay, so we can move on. It's 10:30, so I think we can move on to the surface integrals as well. Okay, so let me raise the board. Okay, so surface integrals. Okay, so the surface integrals we do is, this marker is also out, is something like this. We do a vector function and we integrate that over the surface. Okay, and to do that, we again do the dot product. Okay, so the basic thing, you do v, which is function of x, y, and z dot dA. Okay, so if we do this, we have, and then we integrate it over a surface. Okay, so v is a vector function, a is a surface, and dA is very small, infinitesimal small surface area. Okay, what we do here is we define what is the vector associated with that part of the surface. Okay, imagine we have this overall surface, and this is S. We are doing the integral on, okay? And then this is one small part of the area. Okay, so this is basically the dA that we have here. Okay, how do we define a vector from dA? Okay, the vector on a surface is defined as a vector whose length is proportional to the area of the surface. Okay, the length shows the area, and the directions shows the direction that is perpendicular to the surface. Okay, so this is, you know what, that's not the best drawing of perpendicular, so let me do it again. Okay, so if this is the surface and this is dA, so this is dA as a vector. Okay, length of dA shows the area of A. Okay, the direction is always perpendicular to the surface. Okay, so when you integrate a vector function over a surface, what you're doing is that you're looking at the component of the vector that is perpendicular to the surface area. Okay, so imagine this is dA, okay, and then imagine V is like this. This is V at this point. When we do the dot product, technically we are doing the dot product of V by dA here, and the angle between V and dA matters, okay, and as a result of that, you get a scalar, okay. This integral defined like this on a surface has a name and has a definition that is technically the flux of the vector function V passing through this vector, passing through this surface, okay. Sometimes we look at the flux, we look at the surface integral on a specific surfaces that they are closed, okay, like a balloon, like a sphere, or like a cube, okay. And we do that a lot in electromagnetism as well. That's when we look at the flux of electric field passing through a surface, and if we calculate integral like this, the whole integral is going to be proportional to the charge distribution we have confined within that surface, okay? So the notation for closed surfaces is like this: integral over closed surface v dot dA. And this is again closed surface. Okay. And when you are doing this integral, the trick is that you should really nicely define dA, and you need to be careful what is the direction of dA. Okay, dA is always perpendicular to the surface. Okay. Now you may ask, if it's perpendicular, why did I write this way and not the other way? Okay, this one or this one, okay? And my answer to you is that I don't know, it depends on you. Both of them are somehow correct, okay? There is no correct or wrong way of right or wrong way of doing this. As long as this is perpendicular to the surface, that's fine. But there is one convention, and that convention is that if you are looking this integral on a closed surface, okay? Let's say you have a sphere and you are doing the whole integral on a sphere. Then if you look at dA, okay, if you're on a sphere, and that dA, the direction of the vector should point out outside. It should be outward perpendicular vector to the surface. Okay, so this is the convention that we have for closed surfaces. If it's open surface, it's a bit of ambiguity here. Okay, so I can't tell you what is correct, what is wrong. You just decide what direction you want to calculate flux, and that's going to tell you the flux going from bottom to the top or from the top to the bottom. Okay, and depends on what is the specific application, you will be able to handle it. Okay, you won't be confused, oh, should I do this or that? You will see the problem and you would be able to just easily handle it. Okay. I can tell you in this course we use the closed integrals a lot, okay, not the open ones. And because this is how we measure the flux of electric field over a closed surface, because we want to relate that to the charge distribution, total charge confined in a space, in a volume. Sounds good? Is this clear, more or less? Okay. So there's an example for this one as well. You know, I don't want to do it on the board here, but I suggest you very strongly you do it. It's not difficult, but it has multiple components. So this is like an integral of a vector over surfaces of a cube, okay? So you have a cube like this, okay? The size and dimensions of the cube are defined, okay? And it has components in X and Y and Z. Obviously, a cube is a three-dimensional object. And the question gives you the vector field V, and then you calculate the flux going through each side of the cube. Okay, so it's not difficult at all, but it has multiple steps. I want you to do it on your own, example 1.7, and then you get used to it. Okay, do it. If you have questions, then next time you can ask me questions. Okay, so technically very similar to what we did for line integrals. You have an integral with two vector components, and you should expand them and simplify them to come up with one-dimensional simple integrals, and that's going to give you the number. Okay, here a cube has 6 different surfaces, so you should repeat that on 6 different surfaces. So technically 6 different integrals. Okay, to calculate the closed surface integral of a function on a cube. Okay. Any question? Okay, so I'm going to move on to the next integral, which is the volume integral. Okay, and the volume integral, we do it both on scalars and on vectors as well. The more common way I can think of in this course, we do a lot more with scalar functions than vector functions. Okay, so let's look at that. Integral of, let's say, t dot d tau. The notation in this book, a lot of times, most of the time, we use tau and d tau as an element of volume, okay? And let's say t is a scalar function, okay? So we can have integrals like this, and this integral is a three-dimensional integral, okay? So it could be on a, let's say, sphere, or cube, or any other type of three-dimensional shape, okay? So what happens is that a lot of times this d tau reflects a three-dimensional small volume element. In Cartesian coordinate, that's like xy, dx, dy, dz, okay? So this is a volume of very small cube with sides being like dy, dx, and dz, okay? This is a scalar, okay? T itself is a scalar function. In this case, there is no vector involved, okay? You just integrate that over volume. This is a similar type of integral I'm sure you use to measure, to calculate the volume of, let's say, a sphere or volume of a cube, okay? I'm sure you have done that in calculus. The only difference is that now you have a function, okay, t, which is a scalar function multiplied by that as well, okay? With three-dimensional integrals, the trick is usually you will have now three integrals for x, y, and z. So this can be expanded in terms of like this. Three integrals on x, y, and z. The integrand is t, and then you have dx, dy, dz. Depending on the shape, the limits are very important, okay? If you have a simple cube, the limits are clear, okay? You have x starting, let's say, from 0 to 1, y can go from 0 to 1, and z can go from 0 to 1 as well. And this is going to be integral on a sphere that, sorry, on a cube that the sides are expanding from 0 to 1, okay? Meaning that if this is x, this is y, and this is z, the limits are 1, okay? Now imagine instead of a cube, you are looking at a prism, okay? So we don't have these straight lines here, okay? Imagine you are limited to the case that you cut that cube this way, okay? So this is a still three-dimensional shape. In a way, the limits are still 1, but the fact that you cut it means now you're putting some more limitations on how x should be dependent on y, okay? So for these sort of integrals, what happens is that your y values, okay, doesn't always go from 0 to 1. It goes from 0 to actually the value defined by your x. So it moves this way, okay? So y goes from 0 to 1 minus x. 1 minus x, okay? So you need to be careful when you are doing three-dimensional integrals, not only with the overall limits, but also the limit that is dictated by your shape. And that needs to be reflected in the limits of the three integrals you are doing, okay? And another thing is that you need to be careful which one you are doing first, which one you are doing second, okay? So it's 10:46. I'm gonna stop here. On Thursday, I'm gonna continue this, and I'm gonna do one example of the prism, okay? Just to show that how you why and how you need to be careful to set up the limits and reflect your actual shape in your integral in terms of both the tau and the limits of the components. Sounds good? Okay, we are out of time. If you have any question, I'm happy to answer, and then we can stop it. Any question?
No, thank you very much, Professor.
Thank you, Professor.
Okay. Okay, so on Thursday, I'm continue this, the volume integrals. I will be updating you about the critique file size limit, and we're gonna do one more run test before the actual quiz time, okay?
Sounds
Okay.
good.
Thank you very much. You guys enjoy the rest of your day, and see you on Thursday.
Thank you.
Have a good
Bye.
day.
Professor.